Hi. We are from Group 10. We will talk about FeAl alloy, which is iron aluminium alloy. FeAl alloy is made up by iron and aluminium, which is combined by two of them. And the mechanical properties of FeAl alloy is its density is 5.56 and its exact mass is 82.816 g per mole, and its melting point is 1160 Celsius at 60% aluminium and 1125 250 Celsius at 40% aluminium. Meanwhile, for its strength and ductility of the FeAl alloy, it depends of variety of parameters of four, which is vacancy concentration, environment, alloy, and temperature and grain size.
Okay, now we will continue to the application of iron aluminium alloy in industry. As we know, iron aluminium alloy has such a good corrosion to high temperature. So due to the high temperature corrosion condition as I mentioned before, iron aluminium alloys have been widely used as constructive materials, which is for construction, protective coatings which applied to another material to prevent corrosion, and it is also used for materials working. Iron aluminium also is better compared to other composites of aluminium alloy in terms of high temperature strength. Therefore, it makes iron aluminium alloy as a better alloy that used on spinning components such as gears, shaft, and airplane parts. Next, we will analyze and discuss on the iron aluminium phase diagram. So as we can see here, we will discuss on four different compositions which are 25%, 43%, 80%, and 98% weight percentage of aluminium. So as we know, isothermal reaction normally occurs at the eutectic composition. So from this phase diagram, the eutectic composition is 98% weight percentage of aluminium. This one, 98%. At the temperature of 655 degrees Celsius. So this is where the isothermal reaction occurs. This one at point 2. From this phase diagram also, there are intermetallic compounds that are formed which are FeAl2, FeAl3, Fe2Al5, Fe5Al8. So these intermetallic compounds are formed when there is interface between solid of iron and aluminium, meaning that there are two different solid elements to form intermetallic compound which are iron and aluminium. There are also solid solution from the phase diagram which are solid solution of iron in FCC aluminium, solid solution of aluminium in BCC iron, Fe3Al solid solution, and FeAl solid solution. Next, we will further our discussion to the solidification process for 25% weight percentage of aluminium. As we can see here at point 1, when the temperature around 1500 degrees Celsius, the microstructure of iron aluminium alloy contains 100% of liquid. Then, when the temperature is cooled down to point 2, around 1410 degrees Celsius, it will reach the liquidus line and pass through it. This is where the alpha ferrum or iron starts to form. At this region, the microstructure exists as liquid plus alpha of iron. So then, when the temperature drops to point 3, around 1355 degrees Celsius, it will reach the solidus line where there will be no more liquid. So the microstructure transforms into alpha of iron only in this region, and it exists as solid phase. So after the temperature is being cooled down to around 1200 degrees Celsius, aluminium will start to form and the microstructure will transform into iron aluminium or FeAl. This is also solid phase for the microstructure. Now we will look at the cooling curve and microstructure of the iron aluminium. As we can see here, this is the temperature around 1500 degrees Celsius where it is fully liquid. When the temperature drop to 1410 degrees Celsius, which is the liquidus line here at point 2, we can see the alpha will start to form. And when the temperature drop to point 3, which is the solidus line, around 1355 degrees Celsius, there will be no more liquid and the microstructure transform become fully alpha. And last one, when the temperature drop again until around 1200 degrees Celsius, the aluminium start to form and the microstructure exists as iron aluminium or FeAl. This is solid phase. So the last one, for the phase composition at a specific temperature, which I take here 1200 degrees Celsius. At this temperature, 1200 degrees Celsius, it consists of two phases which are alpha and Fe5Al8 plus FeAl. So alpha is in this left side and Fe5Al8 plus FeAl is at the right side. So to determine the composition here, we will make a tie line like this horizontal line at point 4 here at 1200 degrees Celsius, this tie line, and we will determine based on the weight percentage here. So the composition of alpha ferrum is 79% of ferrum or 21% weight, 21% of aluminium. And the composition of Fe5Al8 plus FeAl is 65% of ferrum or 35% of aluminium. So based on our tie line here, we will calculate the phase fraction for alpha and Fe5Al8 plus FeAl. So based on our tie line, the difference for the left side here is 4 and for the right side here is 10. 25 minus 21 is 4 and 35 minus 25 is 10. So as we can see, alpha here is the left hand side. So to calculate the phase fraction of alpha, the left hand side, the difference for left hand side is 4. So the phase fraction will be 4 over 4 plus 10 times with 100. So we will get 28.57%. So for the phase fraction of Fe5Al8 plus FeAl, which is at the right side, the difference is 10. So 10 over 4 plus 10 times with 100%. So we will get 71.43%. So at this point, the phase exists as solid phase. So we will continue to solidification process for 43 weight percentage of aluminium.
As you can see, for the 43% of alloy, we can the tie line, we can see the solidus process for this. For the 43% is for the point 1. We can see the FeAl alloy has been cooled down from the liquid until it reached at the temperature of 1212 and will become the Fe5Al8, which is, we can see for point 2 that the composition will become the composition will become Fe5Al8 with the liquid, with the measure of liquid, and but the liquid will decrease by the decreasing of the temperature, and it will become fully Fe5Al8 at temperature of around 1200 degrees Celsius, which is, we can see at point 3. But when you reach the solidus line at 1102, we can see the composition of Fe5Al8 alloy will become FeAl and FeAl2, which is, we can see at point 4 after passing through the solidus line at 1102. So for the microstructure and cooling curve for the 43%, we look at the microstructure first. We can see this is the microstructure of F 43% of aluminum of FeAl, which is at the first point. We can see it's fully liquid. Meanwhile, when it reach at the point 2, when it reach up passes the liquidus line, we can see the FeAl, Fe5Al8 have been showing up, have been formed, but in minority. The number of liquid have been decreasing by the temperature, as I've been said. When it reach at point 3, it will become the fully of Fe5Al8. But when it reach 1 at degree of 1102, it will become lamella of FeAl and FeAl2, which is we can see by the cooling curve. We can see the solidus line, which is at 1212, and at the liquidus, I'm sorry, for the liquidus line 1212, and at the solidus line 1200. Meanwhile, when it reached at 1102, it, it will become lamella and will become FeAl2 plus FeAl. For the phase composition at 800 degrees Celsius at 43%, the temperature at the temperature of 800, it consists two phases, which is FeAl and FeAl2, which I've been mentioned before. The composition of FeAl is 66% of Fe. Meanwhile, the composition of FeAl2 is 51% Fe. The phase fraction can be calculated by 9 over 9 plus 6, which is composition over total mix times 100%, which will get 60%. The phase fraction of FeAl2, we use the same equation, and we will get the mass fraction of 40%, and the phase exists as solid.
Solidification process, cooling curve, and microstructure for 80 percentage of aluminium. Iron aluminide are being cooled from liquid to FeAl3 by passing the liquidus line at temperature around 800 degrees Celsius. After passes the liquidus line, FeAl3 will start to form. The FeAl3 will keep performing by the decreasing of temperature. When the temperature reaches the solidus line at 655 degrees Celsius, aluminium will form with the FeAl3 and will keep growing by the decreasing of the temperature. Next, we will go through microstructure and cooling curve of iron aluminide 80 weight percentage of aluminium. At phase 1, the microstructure are liquid, and at phase 2, the microstructure are cementite and austenite. When it reaches phase 3, the microstructure will be cementite, austenite, and perlite. Then at stage 4, the microstructure will be austenite, perlite, cementite, and graphite. The phase composition at 500 degrees Celsius for 80 percentage of aluminium. At the temperature of 500 degrees Celsius, it consists of two phases, which is FeAl3 and aluminium. The composition of FeAl3 is 39% ferrum. Meanwhile, the composition of aluminium is 0% Fe. The phase fraction of FeAl3 are 48.72%, while the phase fraction of aluminium are 51.28%. The phase existed are solid.
Right now, I'm going to explain on solidification process, cooling curve, and microstructure for 98 weight percents of aluminium. At point 1, which the temperature is 1200 degrees Celsius, the microstructure that exists of FeAl alloy is 100% in liquid phase. When it's cooled down until point 2, which the temperature is 655 degrees Celsius, it will reach the eutectic point, which at eutectic point, the isothermal reaction will occur. At this point, the liquid will transform into two solid phases, which are FeAl3 and Al at the same time. When it cools down until point 3, which the temperature is 500 degrees Celsius, the microstructure that exists is the combination of FeAl3 and Al as laminar structure, and at this point, it will transform into 100% of solid phase. This is the microstructure and cooling curve of FeAl alloy at 98% of aluminium. At here, when it 1200 degrees Celsius, you can see that the liquid mixture is cooling until it reached the eutectic line at 655 degrees Celsius. This horizontal line will represent the isothermal solidification of eutectic composition, and this line will represent the solid mixture freezing. For the microstructure, we know that at point 1, it is 100% liquid phase. When it cools down until point 2, there will be liquid mixed with a combination of lamellar structure of FeAl3 and Al. When it comes to point 3, it's completely in solid phase with lamellar structure of FeAl3 and Al. So this is phase composition at 500 degrees Celsius of 98 weight percent of aluminium, which at point 3 the temperature is 500 degrees Celsius and it consists of two phases, which are FeAl3 and Al. So for the composition of FeAl3 is 39% of Fe, meanwhile Al is 0% of Fe. From the timeline here, we can see that the Fe is 37%, while the aluminium is 2%. So in order to calculate the first fraction of FeAl3, we have to divide 37 with 37 plus 2 and times with 100%, and we got that the first fraction of FeAl3 is equal to 94.87%. While for the first fraction of Al, we have to divide 2 with 37 plus 2 and times with 100%, and then we got that the first fraction of Al is equals to 5.13%. The phase exists at this point is solid.
One of the methods to improve the material properties of iron aluminide are precipitation hardening, or it also can be called as edge hardening. So the definition are a heat treatment technique that used to increase tensile yield strength of a malleable material. Metal is edged by either heating or keeping it stored at low temperatures so that precipitate can be formed. This method was discovered by Alfred Wilson. In order to carry out this method, there is the three important steps, which firstly the metal is treated with solution at high temperature. Next, metal undergoes rapid cooling across solvers line, and lastly, material was heated to the supersaturated solution to intermediate temperature. In order to carry out this process without failure, there is three important parameters that must be followed. First one, the solubility must decrease with fall of temperature. Next, alloy composition must be lower than maximum solubility. And lastly, appreciable maximum solubility. The advantages of this process are we can increase the tensile and yield strength of iron aluminide. Next, we can enhance the wear resistance and easy maintainability. Example of the industrial application of iron aluminate that has been treated using this method are the making of engine parts, gears, shaft, aircraft part, and turbine blades.
Another method, in order to improve the material properties of FeAl alloy, is solid solution strengthening. Solid solution strengthening is an attainment of an increase in metric strength through addition of different soluble elements. It is also increased the concentration of transition metal in FeAl alloy. As for the process of solid solution strengthening, transition metal is commonly used as dopants due to low solid solubility and diffusion rate. There are several elements such as molybdenum, titanium, zirconium, chromium, and manganese is added into the alloy and transformed into a ternary alloy with name AlFeX alloys, which X is depends on the element added. There are several advantages of solid solution strengthening, which are by increasing the chromium content in alloy, it will improve the morphology in Al13Fe4, and also it will improve the ductility of alloy at room temperature. By adding manganese, will enhance the structural stability and ductility, and it also increase yield strength and ultimate tensile strength of the alloy. By addition of zirconium, it will improve the ductility, but the effect is depends whether the carbon is present. By using the solid solution strengthening method, there are several applications use it. First is high-speed rotation and moving part in aeronautical and automotive industry, such as gear parts and shaft, and it also widely and commonly used as a component in turbocharger.
In conclusion, we are able to distinguish the mechanical and physical properties such as density, exact mass, and melting point. We are also able to distinguish the strength and ductility with variety of parameters such as environment and temperature. General application in industry are such as construction materials and airpan buds. We also have explained briefly about the phase diagram of variety weight percentage and the acetyl intermetallic compound, solid solution, solidification process, cooling curve, and microstructure. There are also two methods of improving material properties and application that were explained in this video, such as precipitation hardening or H hardening, and also solid solution strengthening.